In this lesson video, we are going to look into vectors and transformations. So as the exams are closer, we are going to look into what are the key pointers that we have to be aware of under these concepts. And also we will be working on some of the past paper questions as well. So in this video, we are going to look into all these three concepts. So vectors in 2 dimensions, translations, and part 3 is magnitude of a vector and vector geometry. So when I say vectors in 2 dimensions, so first of all, if I look into the definition of a vectors, it goes something like this. A vectors means it will have a magnitude and the direction as well. So the magnitude means the length of this line. So whenever we have a normal Cartesian plane or a normal rectangular plane, if I have a point A to be somewhere here, and if I have point B to be somewhere here, so when I say magnitude of AB, so that's just the length of AB. So in a normal rectangular plane, so we can find the magnitude. So magnitude refers to the length here. But we won't be able to say whether this is moving from A to B or B to A. So the directions are not doesn't exist. So whenever we are not talking about directions, we call them as scalar. And whenever we have a magnitude with certain direction, so we call that as vectors. And the vectors will have the tail to be something like this, and this is the point of head. And next, if I look into how do we denote a vector? So if I talk about A to B, we denote it with the vector A. So A with the arrow at the top. Of course, here they have mentioned it in a bold letters, but while writing it, we cannot write it by differentiating the bold letters versus the normal letter. So here it has to be vector A itself. And for any vectors, there will be always two components. One is horizontal component and the second one is vertical component. And here it is going to be vector A is 5 units to the right and 2 units up. We denote it like this. We will also see this in the next slides. If we reverse the direction, then it is going to be equals to negative A. So instead of A to B, so suppose if A to B is vector A, then B to A will be vector negative of A. So now this is what we call it as opposite vectors. Next, and here we are talking about a vector has two components. One is horizontal and the second one is vertical. So the horizontal component is this position. This is what we call it as the horizontal component. And this one we call it as the vertical component. So how many units? And whenever it's plus means in the horizontal component, it refers to it moves 5 units to the right. And whenever it's positive in the vertical component, so that means it will move 2 units up. So this is going to be 5, 2. And this is what we have. And here it's basically B2 A. That's nothing but negative 5 and negative 2. Next, if I look into finding okay, we'll see this later. So first of all, if I look into the transformations, under transformations, mainly we are going to look into translations, rotations, then reflections and enlargement and reduction. So first of all, if I look into translations, translations is basically moving to the left or right or up or down. So the translation happens based on the translation vector. So we will have the translation vector which will define the shape that how many units it has to be moved to the right or left. So translation vector AB is the translation vector here. And here, so if I have the translation vector to be AB, this A would represent the horizontal translation, B would represent the vertical translation. So now, whenever we have any graph, or first of all, if I look into a point, let's say you have a point at 1, comma 2. Let's assume this is point A. Now, if I have to move this point 5 units to the right and 3 units up, so 5 units to the right means here it will be of x coordinate is 6 and 3 units up. So that means the y coordinate would be 5. So this point is going to be 6, comma 5. Now, basically the general rule that you should be aware of is, so whenever you wanted to move any point which is x, comma y, by a translation vector AB, translation, the resultant vector is going to be x plus a, comma y plus 2. Now this is what is the translation vector is. And we can also talk about translation of a shape instead of a point. So suppose if I have a triangle or maybe a square or a rectangle, something like this. And if I want to move this rectangle by a translation vector, by a translation vector 5 and 3. So that means this entire shape should move 5 units to the right and 3 units up. This is what the translation means. And always remember this, translation means the two shapes, whatever we have gotten it. One is the original shape and the second one is the image after translation. So both the shape will be congruent. So that means both shape would be exactly the same. And this is what is about translations. Next, if I talk about reflections, the next thing is we're going to look into reflections. So it could be reflection along any line. So usually you should be knowing it. How do we reflect it in the x-axis, in the y-axis, and also in the line y equals to x. So whenever we talk about reflection in the x-axis, for now, I'll first of all tell you about how do we reflect a point, and reflecting the graph would be, or the reflecting the shape would be exactly the same. So first of all, let me take 3 different things. And the third one, let's say reflection in the line y equals to x. So first of all, reflection in the x-axis. Reflection in the x-axis would be, So suppose if I have a point x comma y here. So when you reflect this point in the x-axis, the resultant point would be somewhere here. So let's say if A is the point, the image of A is A dash, which is after the reflection. So this is going to be the x coordinate remain the same, but the y coordinate changes. So y coordinate you need to multiply it with negative. This is what is the reflection in the x-axis. Then if I talk about reflection in the y-axis, so that means if I have point A here, point A, let me take it as x comma y. And when I reflect this one in the y-axis, the point A dash has to be minus x comma y. The x coordinate has to get multiplied with negative. Next, if I talk about reflection along the line y equals to x, so if there is a point here, which is x comma y, see, always it has to be perpendicular bisector. The line should act as the perpendicular bisector between the point and the image of that particular point after the translation. So another point is here. So this point is going to be y comma x. So it will switch. The x coordinate will become the y coordinate and the y coordinate will become the x coordinate. And this is what is the reflection. And it can also have the reflection in the line x equals to 1, x equals to 2. So whenever we have x equals to some constant, and if we are graphing it, this is going to be always a vertical line. And whenever we have y equals to some constant, and if you graph it, this is going to be a horizontal line. Next, the next thing that we have is rotations. So in rotations, we have this 90 degrees clockwise or anti-clockwise. Then also we have this 180 degrees clockwise or anti-clockwise. So first of all, whenever we talk about 90 degrees clockwise, let's say about the center. So about the center is also very, very important here. So for an example, let's say about the center 0, 0. Let's say C is the center. And we have a point which is 3, 5. Now we have to rotate this one, let's say 90 degrees clockwise. So clockwise means it's somewhere like this. Clockwise means like this. So that means the point would be somewhere here. So the point would be something like, so we can also do it like this distance, and you can use your protractor and find the 90 degrees thing, or you can count the number of x and y steps. The x steps is 3 and the y step is 5. So it will switch. So in rotation, it switches. So switches means instead of 3, 4, 5, it becomes 5, 3. It just becomes like 5, 3. And this is what is the rotation is. And basically the angle between these two lines should be exactly the same, should be 90 degrees. And basically this distance must be the same. And looks like I have drawn it too far, because as it's a rough estimation, I have just drawn it too far. but it should not be too far. So it is somewhere just here. And if I talk about 90 degrees anti-clockwise, the same thing, but I'll be doing it in the other way around. So if I have 3, 5, it switches to 5, 3. So most probably that would work. Yeah. And next, if I talk about 90 degrees, sorry, 180 degrees clockwise or anti-clockwise. So whenever it's 180 degrees, irrespective of whether you're revolving it clockwise or anti-clockwise, it will remain the same thing. 180 degrees clockwise or anti-clockwise. So clockwise or anti-clockwise, it has to be a straight line. So it will be the other way around. So how much ever units that we have it, you need to count it. It doesn't switch. It remains as it is. So this is going to be -3 and 5. So just the quadrant changes. So remaining thing, it would be the same thing. If I look into the enlargement or reduction, the enlargement or reduction mainly depends on the scale factor. So whenever the scale factor is greater than 1, so the enlargement is going to happen. And if the scale factor is less than 1, the reduction is going to happen. So suppose if I talk about the enlarging a particular shape, about the center, is being the origin. So all I need to do is I need to draw this type of line. So basically these 2 points of the rectangle will also lie in this red line. So when that happens, so we need to count it how many steps we have it from center to this particular point. So if it is like 3 steps and 3 steps, so and if the scale factor is 2, then it's going to be 6 steps and 6 steps. So somewhere here, so it would be double of this. And the rectangle would look something like this. This is how the enlargement happens, and the reduction means the rectangle would look something like this. Next, if I talk about stretches, so under stretches, we have the stretches invariant with the x-axis and stretches invariant with the y-axis. So whenever we say invariant with the x-axis, that means the vertical stretch will happen. The stretch would be perpendicular to the x-axis. Let's say if I have the x-axis something like this, and if I have some rectangle something like this, when you do the stretches will happen perpendicular to the x-axis. So that means the stretch figure would be along this line. Suppose if the scale factor is 2, so from this point to this point, if it is 1 unit, it is going to be 2 units. If the scale factor is 2, the graph would look something like this. So this is how the stretch would work. So probably I'll solve the question. At that time, you will understand about the stretches better. And when I say invariant with the y-axis, it would be the other way around. So y-axis would be somewhere here. And let's say if I have some shape, And when I say stretching it, the stretch will happen through these two lines. So let's say if the scale factor is 3, then this is going to be 1 unit means it will be at 3 units. The scale factor is 3 means it would look something like this. And this is how the stretch would work. And next, if I talk about magnitude of a vector. So if I need to find the magnitude of a vector, so that's the length of the vector. Whenever I have any vector which is in the form of vector A, which is in the form of x, y, so then the magnitude of the vector is going to be square root of x squared plus y squared. And here is an example. So if I have vector AB, so it is in the form of 5 and 2, and the magnitude of this vector is going to be square root of 5 squared plus 2 squared. So that's going to result in square root of 29. And whenever the magnitude of a vector is 1, so we say that's a unit vector. And whenever the magnitude is 0, so we call that to be a zero vector. And also, next, if I talk about position vectors. So position vectors means are vectors from origin. So suppose if you have the x and y axis here, and if the origin is here, any vector from the origin. So this vector, we usually denote it as position vector. If A is here, so the position vector, we usually denote it with O to A, O to B, O to C, something like that. So O to A is there. And if I have another position vector somewhere here, let's say this is point B, your OA and OB are the position vector. And if I talk about adding these two vectors, so if I need to find out vector A to B, so now addition of two vectors graphically is, so how can I reach from A to B in the other way around? So if I want to reach A to B, I need to move this A to O, then O to B. So that's basically A to O plus O to B. A to O, so by the opposite vector, we also know this A to O is going to be same as negative of O to A plus O to B. So in general, if I talk about joining any two vectors, vector AB can be always written as O to B minus O to A. So similarly, if I talk about vector CD, so we can also say it out. That is going to be O to D minus O to C. So this is how the position vector would look like and joining two vectors.